Welcome everyone, and let's get right into solving this functional equation. To help us know where to start, let's think a bit more abstractly first. So what's going on is that we need to find such functions f such that when we subtract a linear transformation of f, in particular the transformation 1 minus x, from itself, we get in return a linear polynomial. Even more generally, think about when we can add two functions so that we get a linear function in return. Well, obviously, we can add two linear functions and get a linear function in return. So how about if we want to get at least one solution down, how about we assume that f is of a linear form? And then we can see what happens. So let's try that. Assume that f is a linear function in general. So it's going to have the form ax plus b. Assume that f of x equals ax plus b. Then we need, according to this equation, we know that f of x, which is ax plus b, minus f of 1 minus x, which becomes a times 1 minus x, and we're subtracting b here. This must equal the particular polynomial 2x minus 1, like this. And from this, maybe we can find a and b, or maybe get some system for a and b. And in fact, doing this bit of algebra and noticing also that the b term cancels right away, we get that 2ax minus a is equivalent to 2x minus 1, simply simplifying this left side and keeping the right side the same. So if two polynomials are equal and they have the same degree, which in this case there is, then the coefficients and also the constant term must be equal. So we know that 2a equals 2 and a equals, or minus a equals minus 1. Therefore, clearly a equals 1, while on b, as it got removed here, there should be no restrictions on b. So b is simply any real constant in our case. So if f is a linear function, then this is the solution to it. It is simply going to be x plus a constant. So that is one particular solution to our functional equation. That is certainly not all of them. Think about when else can two functions sum up to be a linear polynomial. Well, maybe the next extension is for a general polynomial. Can two general polynomials sum up to be a linear polynomial? Well, it turns out that yes, and if we try, we find exactly when that is so, and even more so for this particular linear case. So let's assume that f of x is a general polynomial. So it will take on the form of this. It will be an n-degree polynomial with n coefficients. So an, the coefficient an, times x to the n, and then the coefficient an minus 1 times x to the n minus 1, and so on, summed up to the constant term a0, like this. Then we need a form for f of 1 minus x. So then f of 1 minus x, we can simply substitute this 1 minus x into it, and we get that is equal to an times 1 minus x to the n. Ooh, that's a bit complicated to evaluate now. And then summing up, so on, all the way until the constant term over here. And again, as with polynomials, we're going to make an assumption that all the coefficients are real. I'll write that here. And also we assume that they are non-zero. So all ai are not equal to 0. So now we can apply the constraint of our equation and write that f of x minus this transformation of f of x must equal 2x minus 1, but we can obviously simplify their difference by factoring out each of these constant terms. And so we get that the difference is a of n times x to the n minus 1 minus x to the n. Then we're going to add the next constant times the same difference, x to the n minus 1 minus 1 minus x to the n minus 1. And we're going to keep adding all the way until this last coefficient, where we get a1 times x minus this whole thing of a 1 minus x, which just becomes 2x minus 1. And the constant term at the end gets cancelled out. So this right here, not a period, this is going to equal 2x minus 1 by our constraint. Now it should be quite clear that our solution set is very restricted on the polynomials, for we need this whole polynomial to equal this degree 1 or linear polynomial. And polynomials are only equal if their degrees are equal. But it turns out that if f of x is a quadratic polynomial, then f of x minus f of 1 minus x is linear too. For this, we need a note about the degrees of these components. Let k be an integer greater than or equal to 1, and let g of x be this polynomial, which is in fact the component of our difference of functions f and f of 1 minus x. Now consider the degree of the polynomial g. Well, there are going to be two cases. First, if k is odd, then the degree of g will also be k, because notice that what we are subtracting, we're going to subtract, when we expand this 1 minus x to the k, we're going to have an x to the k term with a negative leading coefficient, because from here it is already negative. And when we subtract a negative, we are actually going to add it, and so the x to the k term in the g of x polynomial will be positive and non-zero. So if k is odd, then the degree of g will be k. And as you can already see, if k is even, when we subtract this component of the polynomial, when we expand this 1 minus x to the k, where k is even, the x to the k term will be positive, and so we are going to add it, we're going to subtract a positive term from x to the k already. And the leading coefficient is also going to be 1, for there is nothing inside these parentheses. And so we are going to essentially remove this x to the k term, and we're going to be left with the x to the k minus 1 term with as the leading term of it. So if k is even, then the degree of g is k minus 1. And so now you can see when I'm talking about when f of x is a quadratic, then the difference of f of x and this composition or this linear transformation of it, it will be of degree 1. And so we have to account for a quadratic f of x too. So letting f be a quadratic polynomial, we can get this linear transformation of f, then subtract f of x and f of 1 minus x in order to get, in fact, a linear polynomial, as I showed just now. And when we get this polynomial, it becomes a plus b times 2x minus a plus b. And this must equal 2x minus 1 by our constraint of the equation, and therefore, obviously, a plus b equals 1. And notice the c term canceled out in the process of subtracting, and so c can be any real constant. So we get that another solution set is a quadratic polynomials where a plus b is equal to 1, and c is just a real constant. Note how our solution from the beginning also falls into this set of polynomials. We can simply let a equal 0 and b equal 1, and then c is, as we said earlier, another constant. So now we can write a set of such polynomials. It's going to be quadratic polynomials that will be solutions to our equation. And we will be close to done, but not exactly done, as you will see in a moment. Now I've defined the set P, which is the set of all quadratic polynomials in this form, where a and c are real constants. And as we've shown throughout this whole video, any element of the set is a solution. However, that is not going to be all of our solutions, but we are close. Think about it. We have done this all on the premise of we are adding two functions or subtracting a function from another to get a linear polynomial. And we've assumed that only polynomials subtracted or added can also equal polynomials. But in fact, it happens really easily that two non-polynomials can add or subtract to a polynomial. Just think about this example. Let g of x be this function. I'm going to call it e of x plus x cubed. And let h of x be another function, which is going to be minus e to the x and also plus x cubed. Now, obviously, these are both non-polynomials, but g of x plus h of x cancels out the non-polynomial parts and leaves us with just the polynomial part, which becomes 2x cubed. So clearly, there could be some function f that is non-polynomial and also gives us this. Actually, maybe not, it's not so clear. Maybe there doesn't exist one, but I've solved this problem already. I know it does, and I'll show you why. Let p of x be an element of p, and let h be a function also defined on the reals, such that h of x equals h of 1 minus x. Then clearly, p of x plus h of x is a solution, since p of x plus h of x minus p of 1 minus x plus h of 1 minus x fits our constraint, since h of x minus h of 1 minus x given by the constraint for h becomes 0, and we know that p is a solution. So if we have such a function, then all solutions to our functional equation from the start will be of this form. So now it comes to solving another functional equation. What are the solutions to h of x equals h of 1 minus x? Note that since h is a function, from this equation we can deduce that h of x minus 1 half is equal to h of this whole thing minus 1 half. We're simply subtracting 1 half from both sides, from the input of both sides, which this becomes 1 half minus x. And simply factoring out the minus in here, we get this equal to h of minus x minus 1 half. And notice, it's a very interesting property. If g of x was some function equal to h of x minus 1 half, like so, then we see that g of x equals g of minus x. And in fact, this is about as low as we can go for this functional equation because there is a special name to such functions satisfying this identity. They are called even functions. Surely some of you know this fact. And for even functions, we don't really have a solution. This is also a functional equation, technically, just we didn't solve it, we just named a whole class of functions that satisfy this identity, even functions. So as we can see, h of x is simply an even function that is shifted 1/2 units to the right. In fact, these functions are called special names. Even functions that are shifted are called symmetric about their shift. Well, because even functions, by basically their definition, they are symmetric about the line x equals 0. And so if we shift it by, in this case, 1/2 to the right, this makes h of x any function that is symmetric about x equals 1/2. So that is really our solution to h of x, functions that are symmetric about that line, because we can't really solve that analytically for some certain case of functions. There are several functions, uncountably infinite, that are that way. So that brings us to our final solution. If p of x is in the set of p, which we defined, and h of x is any function that is symmetric over the line x equals 1/2, then p of x plus h of x is a solution. And that, I believe, is all of the solutions. I'm not too sure. I've tried checking a bit more. I've tried doing some more methods. But I think this is quite general, and this will get you quite far for the solutions in this functional equation that we had from the start. Thank you all so much for watching. I hope you enjoyed this functional equation. And if you are still watching, make sure to come back to this channel next week. I have an amazing video planned on Buffon's needle, the infamous experiment about dropping needles on grids and approximating pi that way. So that is it. Goodbye.